Hi everyone, welcome to GoClasses. In this session, we will study relation revision. We will see the revision of relations and also the GATE previous year questions from this topic relations. Okay, so let's start now. Let me introduce myself. My name is Deepak Poonia. I have post graduated from IIC Indian Institute of Science Bangalore, and multiple times, I have secured top rank in the GATE exam like All India rank 5367, 206, 256, etc. And also discrete mathematics complete course is freely available for all the students. Okay, the complete discrete mathematics course is free for all the students on the GoClasses website. Okay, so go to the website and you can start your preparation. Let's start the session now. So the session is summary of relations. So first of all, in the relations, what is very important thing, that is the concept of ordered pair. Okay, the concept of ordered pair is very important in the relations. So what is the concept of ordered pair? We already know that a set is in a set order does not matter. So if I give you a set A comma B, this is same as set B comma A. So remember, in a set order does not matter. Okay, but what is the ordered pair? Here order matters. Here order matters means A comma B is not equal to B comma A. Okay, so you can see that in a set, if I give you a set 1 comma 2, there are two elements in this set. This is same as 2 comma 1, right? Because order does not matter. But remember, in a ordered pair, these two are not same. This 1 comma 2 ordered pair, and we write like this in a parenthesis. So here you can notice we use this symbol. We use this symbol for set. We use this symbol for set, and we use this symbol for ordered pair. Okay, so sorry for that. We use this symbol. So in ordered pair, we use this symbol parenthesis. So this symbol we use for ordered pair. Okay. Now you can see that this 1 comma 2, this is not same as 2 comma 1 because order matters. And also a few things I also want to tell you, that in a set, you know that this set 1 comma 1, this set is same as this set. Both are basically same. Okay. So the repetition does not matter. But remember, in a ordered pair, what matters? In this concept of ordered pair, in this structure of ordered pair, what matters? This also matters. So remember, this is not same as this. These are not same. Okay. So again, very simple, this concept of ordered pair, this is very important for the relation. Now let's move on. The Cartesian product concept we have already seen in the last lecture. You can watch it. What is a Cartesian product? So if you have a set A, you have a set B, then what is Cartesian product? What is A cross B? A cross B will be basically set of ordered pairs. Remember, in this you will have ordered pairs where the first element will come from A, first element will come from set A, and the second element will come from set B. So this is the concept of Cartesian product. Like you can easily see that if this is your set A, your set A has two elements. This is one element, this is another element. So two elements in your set A, and your set B has two elements. Then what A cross B will be? You can notice in the A cross B, the first every element will be ordered pair. You can notice every element is ordered pair. First element is coming from A, you can notice, and the second element is coming from B, you can notice. Okay, so you can notice every element in the A cross B, in this A cross B, every element is an ordered pair where the first element is coming from A, second element is coming from B. You can notice this C comma D, this is an element here in the set B. So again, you can notice that this is a ordered pair. In this ordered pair, the first element is coming from A, second element coming from B. You can notice this is an ordered pair, first element coming from A, second element coming from B. So like this. So this is the concept of Cartesian product, cross product. Now let's see what is the concept of relation. What is the relation from set A to set B? So relation from set A to set B, it means elements of A, elements of set A, they are related to remember, they are related to elements of set B. This is the simple concept. For example, you can see here you have a set A which has three elements 1 2 3. Set B has two elements 5 6. Now we have a relation from set A to set B. We have a relation. So we have a relation R, and in this relation you can notice that element of A, set A. So you can note there is a relation from set A to set B, and in this relation what happens, that this elements of set A, they are related to elements of set B. Like this one is related, I can say that 1 is related to 5 under this relation R. You can notice 1 is related to 6 under this relation R. 2 is related to 5 under this relation R. You can notice that 2 is not related to 6 under this relation R. So what we do this cross. like here, okay, like this. So it means that 2 is not related to 6 under this relation R. Again, you can notice that 3 is related to 5 under this relation R, and you can notice 3 is not related to 6 under this relation R. Okay, so very simple. Now so this is a relation from set A to set B. Okay, elements of A, they are related to elements of B. Now let's see this example. In this example, you have a set A which has 4 elements, 1 2 5 7. There is another set B which has 4 elements, A C M N. Now you can notice there is another relation from set A to set B. There is another relation. This is a relation, let's call it R1. So this is relation R1. Now you can easily see that one is related to C under this relation R1. Under this relation R1, this one is related to C. You can easily see that one is not related to A under this relation R1. So I can cross it. Okay, you can easily see that one is not related to M under this relation R1. So I can cross it. So like this and so on. Now the another representation for the same thing, remember, when you write like this, for example, let's assume there is a set A and there is a relation from set A to set B. There is a relation, and in this relation, let me assume that this is your set A, this is your set B, and some element you have, for example, some element X you have, and that is related to Y. Then what we will write? We will write that X is related to Y. Either you can write like this, or you can write like this, that X comma Y, this ordered pair belongs to R. Okay, this ordered pair belongs to R. It means X is related to Y. Okay, so either you can write like this or you can write like this. So both are same. Now similarly, for example, if X is related to Z also, then we will write that, okay, X comma Z, this ordered pair belongs to R. Now similarly, if let's assume this X is not related to M, then we will say that this X comma M, this does not belong to R. This does not belong to the relation. And similarly, I can also say that X is not related to M under this relation. I can also say that X is related to Y under this relation. X is related to Z under this relation. So these two things are same. Okay, this I can say that, remember, this and this, they are basically same. They are basically same notation. Either you can write like this or you can write like this. They are both basically same. Similarly, for example, here, these are basically same. You can write in any way. Okay, either you can write like this or you can write like this. Anyway, let's move on now. So this is the concept of relation from set A to set B. So you have two set A comma B. Binary relation. Binary relation means this is between two set. Okay, they can be same or different. Binary relation it means between two elements. Okay, binary relation, it means basically two elements. For example, here you can notice these are two elements, as you can see, like, okay, two elements, between two elements. So binary relation means between two elements from set A to set B. That is a subset of A cross B. Okay, so basically every relation, if you have a relation from set A to set B, then this is very important. This relation, you can easily see that in this relation, elements of A will be related to elements of B. Okay, in this relation from set A to set B, you have this relation R, and in this relation, what will happen? Elements of A, those will be related to elements of B, and so on and so on. Now you can clearly see that what is the largest relation you can create? The largest relation you can create is every element here is related to every element here, and that is your A cross B. In the A cross B, what happens? In the A cross B, when you do this A cross B, remember, when you do this A cross B, then what happens? Every element here will be related to every element here. Every element here will be related to every element here. So you can notice this is what happens in the A cross B. Now I can say that every relation is basically a subset of A cross B. So this is a simple point. You have a relation from A to B, that is a subset of A cross B. So it simply means that this relation contains ordered pair. This simply means that this relation will contain ordered pairs. Okay, it will contain ordered pairs, right? Because this is a subset of A cross B, and you know what is A cross B. A cross B is the set of ordered pairs, set of all ordered pairs where first element is coming from A, second element is coming from B. So this is your A cross B. Now every relation from A to B, that is a subset of A cross B. Now let's move on. So you can easily see these are the examples, like between set, this type of relation you can define. Okay, you can define the subset relation, superset relation, many type of relations you can define between set. Okay, between numbers you can define like less than equal to, this relation you can define this less than equal to this is less than equal to, these are the different relation. And this is basically x modulo k is equal to y modulo k. This is the modulo k relation. Now tell me the answer for this. Tell me the answer for this. So for example, if your relation, you can see that this is a relation less than, then in this situation, can I say this is related to this? 10 is related to 12. Can I say? Can I say 10 is related to 12? Your relation is less than. So can I say 10 is related to 12? The answer is yes. Okay. So because 10 is less than 12. Next, you can notice 5. Can I say 5 is less than minus 2? So you can see no, this is not related. You can notice that 5 is not related to minus 2. Next, let's see this. Can I say 7 is congruent to 10 modulo k, modulo 3? Can I say 7 comma 10? Can I say they are congruent to modulo 3? Can I say 7 comma 10? Can I say that they are congruent to modulo 3? Can I say? The answer is yes. Okay, because if you divide this 7 by 3, then the remainder will be same as when you divide this 10 by 3. Okay, so basically 7 comma 10, they will give you the same remainder when you divide by 3. Okay, so that is the reason we say that 7 comma 10, these are congruent to modulo 3. Okay, these two 7 comma 10, these are congruent to modulo 3 because they will give you the same remainder when you divide by 3. Okay, the remainder will be 1. So yes. Next, let's see this. What about 6 comma 11? So will they give you the same remainder when you divide by 3? When you divide by 3, will they give you the same remainder? The answer is no. So they are not related because this will give you remainder 0, this will give you remainder 2. Next, let's see this. So you can easily see that if A is related to B, you have some relation R. If A is related to B, then you can say A is ARB, or you can also say that A comma B will be, or you can also say like this. You can say that A comma B that belongs to R. Similarly, if A is not related to B, then either you can cross it, or you can say that A comma B does not belong to R. So this is your relation. This is the relation. Now let's see. Most of the time, remember, most of the time we are interested on the relation which are from A to A. Okay, most of the time we are interested in this type of relations. This type of relations are very important, where where elements of A, they relate to elements of A. Okay, elements of A are related to elements of A. This type of relations are very important, and we call them, what we call them, we call them that you have a relation on set A. This is very important. This is very important that you have a relation on set A. So if you have a relation on set A, it means that elements of A are related to elements of A. You can notice elements of A, they are related to elements of A. So this type of relation is called, you can notice, relation R on set A. So this is very important. For example, if I ask you, you have a relation, when I say you have a relation on set, on or over, you can either you can use this or you can use this. Like if I say you have a relation on or over set A, then what it means, then what it simply means, then remember this is same as that a relation, this relation is from A to A. Okay, elements of A related to elements of A. Now let's check this. I can also say that this R, this is a subset of A cross A. Okay, so all these things are same basically. This R is a subset of A cross A. Okay, so this is very important. Here basically this relation is on set A, so this set A is basically your base set. I can say that this set is basically the base set, and I can say your relation is from set A to set A, or you can say that this is a subset of A cross A. I can also say that this R, this is basically, what is this relation R? This is basically like this. Okay, in this relation R you have X comma Y, where X also comes from A, where Y also comes from A, and there is some condition, that X should be related to Y. Okay, there is some condition that X should be related to Y. But you can notice that in this relation R, you will have ordered pairs where the first element will come from A, this first element will come from A, the second element will come from A. So this type of ordered pairs you will have such that X is related to Y. So all these things are same. Okay, all these things. For example, if I say that you have a relation on set N, okay, set of natural number. If I say that you have a relation on set of natural number, then how will you say set of natural number? Then you will say that from natural number to natural number. It means you have a subset of N cross N. It means that in this relation R, you will have ordered pairs where the first element will come from N and the second element will also be natural number, such that X should be related to Y. Okay, very simple. Now one more thing I want to tell you. You tell me a simple thing. If I give you this, if you have a relation R, let's assume you have a relation R on set A cross B. What it means? Tell me. Okay, on set A cross A. Let's see this. So tell me what this means. you have a relation R on set A cross A. What this means? Does it mean this? Okay, which is correct? Which is correct? Like first, is this correct that this is a relation from set A to set A? Or is this a relation from A cross A to A cross A? Which is correct? Okay, so you can easily see that this is not correct, this is correct. Okay, this means you have a relation on set A. Okay, it means this relation is on set A. So remember, this is not correct, the second one is correct. Okay, this one is correct. So I hope this point is clear. Now let's see, if you have a relation on set A cross A, then in this situation you can also say like this. You can also say that this is from A cross A to A cross A, elements of A cross A. Remember, these elements will be related to these elements. Okay. You can also say that this is a subset of this relation R. This is a subset of A cross A cross A cross A cross A cross A. Okay. Next, you can also say that in this relation R, you can also say what you can say. You can say that in this relation R, what you have? In this relation R, you have ordered pairs. Okay, in this relation R, you have ordered pairs x comma y, such that again this x will come from A cross A, this y will come from A cross A, and this x must be related to y. Okay, there will be some condition, and this x must be related to y. Okay, so I hope all these points are very clear, because these are very important. Many students cannot find out the base set. Here, this is the base set. So remember, in this is the base set. And for example, if you write like this, here this is the base set. So many students, they cannot find out the base set. They get confused what is the base set. For example, if I give you this, if I give you this question, like you have a relation R and consider this relation R is like this. So let me assume that this relation is like this. Okay, A comma B related to C comma D. Okay, let's assume this is your relation. Maybe this A comma B comma C comma D, they all belong to set A. Okay, they all belong to set A. And for example, I can say maybe A should be less than C and B should be greater than D. So this is your relation. Now in this situation, tell me what are the base set. For this relation, what is the base set? Simple question I am asking. For this relation, what is the base set? What is the base set for this relation? So you can notice in this relation you have ordered pairs. Okay, where? So you can notice this A comma B, this is related to C comma D. So you can easily see that the base set will be A cross A. Okay, this is the relation from A cross A to A cross A. You can notice this is element of A cross A. Okay, this is element, this is element of A cross A. You can notice. So element of A cross A is related to element of A cross A. So here the base set is basically A cross A. So this relation R, this is basically from A cross A. Elements of A cross A are related to elements of A cross A. Okay, so this is a simple point, that what is the base set, finding out the base set. Okay, so always understand the base set first. Before you study, before you solve any question related to the relation, first you understand what the base set, on which set the relation is defined. Okay, now let's move on. So you can easily see, if you have a relation on set A, then it simply means that this is a subset of A cross A. It will be from A to A. Okay, now let's move on. Binary relation basically means that it is a relation between two elements. Okay, between pair of elements. So this is the definition of binary relation. You can have, like in the DBMS, you have I can say non-binary relation. Okay, you have n-array relation, or also you can have in the DBMS subject you have this type of relation, like I can say n-array relation. So this type of relations also you can have, of course. In these relations, what will happen? N-array relation R. So in this relation, what will happen? In this relation, you will have basically, you will have n tuples. Okay, in this relation you will have n tuples like this. So you will have n tuples, such that where this AI, it is coming from some set. Okay, it is coming from some set and there is some relation. So like this. So this type of, basically this type of relation is called an array relation. An array relation means there are many sets. Okay, so for example, maybe this is coming from set A, this is coming from set A1, this is coming from set A2, and so on, and this is coming from set AN. Okay, so this type of relation is called an array relation. Okay, anyway, most of the time this binary relation is important. Most of the time they will ask you this is very important. So most of the time they will ask you the relations which are on set A. Okay, which are on set A. So this type of relations are basically, okay, this type of relations are basically from A to A, or you can say that this type of relations are basically subset of A cross A. In this type of relations, you will have ordered pairs. Okay, now let's move on. So very simple. Now let's see the representation. If you have a relation from set A to set A, okay, from set A to set A, then what are the representation? The representations are either you can have graph representation or you can have matrix representation. Let's see the first one. So you can easily see here, you have a set 1, 2, 3, 4, and the relation that you are defining, that is a divides relation. So A divides B. Okay, A is related to B if if and only if A divides B. And okay, on this set you have this relation. So you can easily see that your base set, understand that your base set is 1, 2, 3, 4. This is your base set, and on this you have a relation R on set A. What it means? It means that you elements of A will be related to elements of A. It means that R will be subset of A cross A. Okay, and the relation, what this relation is saying, this is saying that X is related to Y if and only if X divides Y. Okay, if and only if X divides Y. This you can also write like this. This you can also write like this. This symbol is the symbol for divides relation. This is the divides relation symbol. Okay, so you can also write like this. Now let's see what are the representations. The one representation, you can easily see that one will divide one, right? Okay, so 1 is related to 1. You can notice 2 is related to 4 because 2 divides 4. Okay, you can easily see 4 is not related to 2 because 4 does not divide 2. Okay, so very simple. So here what you can do a graph representation. In the graph representation, you will create nodes for every element of the base set. So here this is the base set. So in the graph representation, what you will do, for every element of the base set, you will create one node. And now you can notice 3 is related to itself, 2 related to itself, 1 is related to itself, 4 will divide itself, 1 will divide 3, 1 will divide 2, 1 will divide 4. Okay, and you can notice 2 is related to 4, and you can, that's it. Okay, so 2 is related to 4, so that's it. So this is your this is the final graph. You can check it. This is the graph representation, and in this graph representation you can easily see 4 is not related to 2. You can notice 4 not related to 2, but 2 is related to 4. You can notice 1 is related to 3, but you can notice 3 is not related to 1. Okay, so very simple. And you can notice 2 is not related to 3 and 3 is not related to 2 because 2 does not divide 3, 3 does not divide 2. Now let's see the matrix representation. The matrix, this is called graph representation. This representation is called basically the graph representation. In the graph representation, what we do, for every element of the base set, we create a node. Okay, so this is the graph representation. Now let's see the next, that is matrix representation. In the matrix representation, what will happen? It will happen that you will put the these elements you will put in a matrix format, 1, 2, 3, 4, 1, 2, 3, 4. In the matrix format you will put them, and then you can notice 1 is related to 1, 1 is related to 2, 1 will divide 3, 1 will divide 4. Next you can notice 2 related to 2, 2 related to 4, 3 related to 3, 4 related to 4. So this will be your matrix representation. Okay, so this matrix representation you can also write like this. If you don't want to write like this, you can also write in the terms of 0, 1. You can say that 1 is related to 1. It means, okay, so you can write 1, 1. 2 related to 2, 2 related to 4, 3 related to 3, 4 related to 4. So like this also you can write. Okay, the remaining entries will be 0. The remaining entries, those will be 0. So like this also you can write. This is the matrix representation. Here also the remaining entries will be cross. Okay, so either you can use cross or tick mark, or you can use 1, 0. So you can use this also. So this is the matrix representation of a relation. Now let's see the next. For example, this is your base set and your relation is not equal to. Okay, so you can easily see that 2 is related to 4 because why 2 is related to 4? Because 2 is not equal to 4. Okay, so you can notice the relation is A is not equal to B. So you can notice 1 is related to 3 because 1 is not equal to 3. Now you can notice 1 is not related to 1 because 1 is you can notice 1 is equal to 1. So this will be the graph. Okay, every element will be related to another element. Okay, but it will not be related to itself. Like you can notice that 4 is not related to 4. So but you can easily see that 4 is related to 3 because 4 is not equal to 3. So this is the relation not equal to, and this is the graph representation. Now the next, the matrix representation also you can create. The matrix representation for the last graph that will be 1, 2, 3, 4, 1, 2, 3, 4. The matrix representation will be like this. So 1 is related to 2, 3, 4. 1 is not related to 1. 2 is related to 1, 3, 4. It is not related to. So you can notice the graph will be something like this. The matrix representation will be like this. You can notice all these will be 0. The remaining elements are 1. Okay. This is the matrix representation of this relation R. There is a relation R, and this relation R is basically from set A to set A. Okay, where set A is already given to you 1, 2, 3, 4. This is the set A, and the question is saying that X is related to Y if and only if X is not equal to Y. Okay, so this is the graph. This is the matrix representation of this relation. Now the next is, on this set you have this relation equal to. Now you can easily see that 1 is related to 1 because 1 is equal to 1. You can easily see that 2 is not related to 3 because 2 is not equal to 3. Okay, so this is the relation A equal to B, and the graph representation will be this. Everyone is related to itself. Okay, now the next, let's see this question. Quickly tell me the answer. This is a Stanford question. So can you tell me the answer for this question? This question is taken from the Stanford University. Most of these slides are also taken from the Stanford University. Like this slide is also taken from the Stanford University. So the source is Stanford University. Tell me the answer. Okay, let's see this. So the question is saying that below is a picture of binary relation R over the set 1, 2, 3, 4, 5, 6, 7, 8. Okay, so these are the elements 1 to 8. Okay, so you have a relation R. Very simple that you have a relation R from set A to set A, and this is this set A. What is this set A? This set A is basically 1, 2, and so on 8. Okay, this is your set. So from set A to set A, you have a relation, and this is saying which of the following is correct definition of the relation R. For this relation R, which of the following is a correct definition? So you can easily see this is not a correct definition because this is saying that X is related to I, X is related to Y if X is equal to 3 and Y equal to 5. So this is definitely not correct because you can easily see that here 5 is related to 7. Okay, you can notice 2 is related to 4. Okay, so definitely this is not correct. Now the next is saying that X is related to Y. X is related to Y if Y is equal to X plus 2. Okay, so yes, that is correct. That is correct. Okay, so because you can easily see 2 is related, 1 is related to 3. You can see 1 is related to 3, 2 is related to 4, 3 is related to 5, 4 related to 6, 6 related to 8, 5 related to 7. Okay, so you can easily see that this is correct. Okay, if you see every element, then every element is basically related to every element X is related to Y, where Y is equal to X plus 2. So this is correct. What about the next? What about this one? This is not correct. This is saying that Y is related to X, then Y is equal to X plus 2. This is false. Why? Because you can easily see that 4 is not related to 2. Okay, 2 is related to 4, 4 is not related to 2. So the answer for this question, the answer will be option B. Okay, very simple. Now let's see the next. So what are the types of relations? So for any relation, you can have many different properties, or I can say types of relation. Either you can call them property of relation, or you can call them types of relation. That does not matter. So there are some types of relation. Those are, for example, this type of relation where every element is related to itself. Okay, this type of relation, you can notice A is related to A. This type of relation are called reflexive relation. So what we call them, this type of relation, you can see this type of relation, we call them reflexive. This is the property of being reflexive. Okay, so this will be reflexive if for all the elements A in the base set, this happens. Okay, for all the elements A, for every element, this should happen that it is related to itself. Then this we will call that this is a reflexive relation. Okay, in this situation. Now the next property is saying that if A is related to B, then B should be related to A. Okay, if this happens, A is related to B, then B should be related to A. This should happen for all A comma B. Okay, so for all A comma B, this should happen for all A comma B belonging to base set. So this should happen that if you are related to B, remember, if A is related to B, then B should be related to A. Okay, so this type of relation will be called symmetric. There is a symmetry here, so this will be called symmetric relation. Symmetric relation means if A is related to B, this is very important. This is if this happens, then this will happen. Okay, now let's see this. Next property is if A is related to B, B related to C, then A should be related to C. Okay, so if this happens, If this happens, A related to B, B related to C, then this would happen, A related to C. This property is called transitive relation. This is the property of being transitive. So we will call that this is a transitive relation. So these are the three properties. So you can notice, if this happens, that every element for all A, so you have a relation, let's assume you have a relation from set A to set A. So this is the relation. Now, for all A, if this happens, that A is related to A, then what we will say? This type of relation, we will say that R is a reflexive. Okay, R is a reflexive relation. Now, here you can notice, for all A, for all B, this would happen that if A is related to B, then B is related to A, then this type of then we will say that R is a symmetric. Okay. Now the last is for all A, all B, all C, this would happen that if this happens, A related to B, B related to C, okay, A related to B, B related to C, then what should happen? Then this would happen that A should be related to C. This is called transitive property. So you will say that R is transitive. Okay, in this situation you will say R is transitive. So very simple, these are the types of relation. I hope you understood. Now what is this reflexive property? Reflexive property means every element is related to itself. Okay, every element is related to itself. So for example, you can notice this is a reflexive relation, x is equal to x for any x. Yes, every element is equal to itself, every set is subset of itself, every element is congruent modulo k to itself. Okay, so very easily that all these relations are reflexive because every element is related to itself. Like for example, here you can notice this is the reflexive property, every element is related to itself. These are the, you can note, these are the self loops. Okay, so these self loops, they tell you that every element is related to itself. So this is a reflexive relation because remember, very important, every element is related to itself. Now for example, this, tell me the answer for this question. What is the answer? A simple question I am asking. Let R be a binary relation. Again, this is a Stanford question. So tell me the answer for this. Let R be a binary relation by this drawing. This is the drawing of relation R. So basically this is your relation R. The question is saying this is the relation R. Now the question is saying that how many of the following objects are reflexive? How many of the following objects are reflexive? This is the relation R. How many? Okay, some objects are given to you. The first object, the second object, the third object, fourth object, fifth object. Tell me which object is reflexive? Tell me which object is reflexive? Which object is reflexive? So you can notice R is not reflexive. Okay, R is not reflexive because this relation is not reflexive because you can easily see that this element is not related to itself. And the answer is not this also, not this also, not this also, not this also, because reflexivity is a property of relation, not of an element. Okay, so this is a question from the Stanford University, and this question is basically just to remind you that reflexivity is a property of relation. Reflexivity, remember, this is a property of relation. It's not like like this is reflexive, this is not reflexive. It's not like that. Reflexivity is a property of relation. So please understand that reflexivity, this is a property of relation, not of individual objects. Is this understood? Let me know. Okay, let me know. Is this clear? So this is not a tricky question. Don't worry that in the GATE exam they will not ask you this. Okay, this is just for your understanding. In the GATE exam they will not ask you this. In some hulu test series they can ask you this, but this is for your understanding that reflexivity, this is a property of relation, this is not a property of individual object. Yes, you can say that this is not related to itself. Okay, for example, if I say this is A, this is B, this is C, this is D, yes, this is fine. Like A is not related to A, this is fine. A is not related to A. B is related to B, C is related to C, D is related to D. Okay, so this is fine. But like for a particular object, you cannot say that this is reflexive. For a particular element, you cannot say that this is a reflexive. Reflexivity is a property of relation, not of individual object. Now let's move on. Now let's see this symmetric property. Symmetric property says that if, this if is very important. This if is very important. If A is related to B, then B should be related to A. Okay. So for all the elements, I am saying that if A will help B, if A is helping B, then B will help A. Okay, if A is related to B, then B will relate to A. So in this type of relation, basically the order of objects does not matter, right? Yes or no? Like for example, you can easily see that order of object does not matter. For example, if I say, like I can say that, for example, 4 is equal to 4, so the order does not matter. Okay, so you can also write it that 4 is equal to 4. So in this type of situation, order does not matter. For example, I can say that 4 is congruent to 7. 4 is congruent to 7 modulo k. 4 is congruent to 7 modulo 3. Okay, so this is also, you can also say that 7 is congruent to 4 modulo 3. So both are basically same. So in this type of relation, what happens? The order of object, basically that does not matter. This type of relation are called symmetric relation. Symmetric relation means if A is related to B, then B should be related to A. Like for example here, if this is related to this, this should be related to this. If this is related to this, this is related to this. So like this. This is your symmetric relation. Now let's move on. Tell me the answer for this question. Tell me the answer for this question. Let me know. So is this relation symmetric? Is this relation symmetric? No. This relation is not symmetric, because you can notice this is related to this, but this is not related to this. Okay, so you can see that this is not a symmetric. This relation is not symmetric. You can easily see that A is related to B, but B is not related to A. So you can see that A is related to B, but B is not related to A. So this is not symmetric. Symmetric says that if A is related to B, then B will be related to A. Now let's see this. Is this symmetric? Yes, this is symmetric, right? Because you can easily see that if A is related to B, then B is related to A. So yes, this is symmetric. Okay, so is this relation symmetric? The answer is yes. Now let's move on. Transitivity. Transitivity says that basically you can change the elements. Transitivity says that if A is related to B, B is related to C, then what should happen? Then this should happen that A should be related to C. This is called transitive edge. Okay, this is called transitive edge. This type of edge is called transitive edge. Okay, so because here A is related to B, B is related to C, then this should happen that A is related to C. This type of edge is called transitive edge. Very similar. Okay, very simple definition. So now let's move on. So let's see this. The transitivity graph will be like this. You can notice this is related to this. Okay, this is related to this. This is related to this. Then you can notice this will be related to this one. Okay, so very easily you can see. For example, you can notice this pink is related to yellow. Yellow is related to blue. And now you can notice this pink is related to blue. Okay, so very easily you can see. Now let's move on. Is this transitive? Is this relation transitive? Look at this relation and tell me, is this relation transitive? Yes, this relation is transitive. There is no problem, because you can easily see that transitivity says that if it is related to this, and if this is related to that, then this yellow should be related to this one. Okay, but here you can notice there is no violation of transitivity. So is this transitive relation? The answer is yes. Okay, is this relation transitive? The answer will be yes. This relation is transitive. Okay, so you can easily see that this is a transitive relation. So there is no problem here. Now tell me the answer for this question. Is this transitive? Tell me. Is this transitive? This relation, is this transitive? Look at this and tell me, is this relation transitive? So the answer is clearly no. This is not transitive, because if you consider this as element A, element B, then what will happen? You can notice that A is related to B, B is related to A, but you can notice that A is not related to A. Okay. So similarly, B is related to A is related to B, but you can notice B is not related to B. Okay, so this is not transitive. This relation is not transitive. Very easily you can see. Okay, and this is the problem. So now what you can do, if you want to make it transitive, then what you can do, then you can do like this. Okay, if you want to make it transitive, you can do this and this arrow you can put. Now this will be transitive. Now this is going to be transitive. So very important thing I am telling you, what is the graph? Let's see the graph of reflexive. Okay, the graph of reflexive relation, what that will be? The graph of reflexive relation will be like this. Okay, for every node, what should happen? For every node, what should happen? For every node, there must be self loop. Okay, for every node, we must have a self loop. So very important, for every node we must have a self loop for every node. Okay, whatever node you take, we must have a self loop. This is called reflexive property. This is the graph of reflexive. What is the graph of symmetric? What is the graph of symmetric? If this arrow is there, if this arrow is there, okay, then this arrow also must be there. Okay, if this arrow is there, if you have this arrow, then this arrow also must be there. Okay, so bidirectional edges, you must have this type of situation. Bidirectional, all the edges must be. For example, if you have this situation, then this situation must happen. But remember, this is fine. For example, this z is not related to this, is fine. This graph is symmetric. Okay, so this is a symmetric relation. This graph is a graph is for symmetric relation. This is perfectly fine, no problem. Okay, this is also fine. Like for example, if you have some element m and that is related to itself, this is for symmetric relation. Now let's see for transitive. For transitive, what will happen? For transitive, what will happen for transitive? This is very important, that for transitive what should happen? If this happens, a b, if this happens, okay, then definitely this should happen. Okay, then definitely this should happen. So if a related to b, b related to a, then definitely a should be related to a, b should be related to b. This is your case one. Okay, very important, this is your case one. The second case is basically, this is your case one. The second case is, you have a, you have b, you have c, and let's assume that from a you have b, from b you have c, then this also must be there. Okay, then this arrow must be there. Okay, so this is your another case. So these are some cases I am telling you, some cases where transitivity, how to check for transitivity. So these are some cases that I want to tell you. These are very important. Okay, this many students they miss this. Let me tell you, many students they miss this. They will miss this. If a is related to b, b related to a, then remember this should happen, that a should be related to a. Okay, this should happen. Many students they miss this one. This one many students will capture, but this one many students will miss. Okay, so anyway, now let's move on. Now let's see this one, equivalence relation. What is the equivalence relation? Equivalence relation is a relation which has all these three properties. It should be reflexive, it should be symmetric, it should be transitive. All these three properties must be there. Okay, reflexive, symmetric, and transitive, all these properties must be there. Then you will say that relation is equivalence. So which properties equivalence relation must have? So all of them, this also, this also, this also. Okay, so all these properties equivalence relation must have. So if you have all these three properties, then the relation will be called equivalence relation. Okay, so for example, you can see this one, like you have a relation, this is a relation, let's call it R. Okay, like this question you can check, this question you can check, there is a relation, let's call it R. Now what this relation is saying? This relation is saying that this is over set of integers. It means that this is a relation from set of integers to set of integers. Okay, it simply means that this relation is a subset of z cross z. Okay, because this is on z. Now this is saying that a is related to b if a plus b is even. You can easily see that this 0 is related to 4, 1 related to 9, because 1 plus 9 is even, 2 related to 6, 5 related to 5. Okay, so you can easily see. Now tell me, is this reflexive? Is this reflexive? This relation, is this reflexive? Like you are saying that you have a relation from set of integers to set of integers, and you are saying that x is related to y if and only if x plus y is even. Okay, so tell me, is this reflexive? On set of integers, yes, this is reflexive. This is clearly a reflexive relation, because every element will be related to itself. You can easily see that a plus a, that will be even. Okay, that will always be even for all a. Okay, for all a in the set of integers, this will happen. This will happen. Now let's see the symmetric property. Is this symmetric? Yes, this will be symmetric, because you can notice if a plus b is even, if a plus b is even, then definitely b plus a will be even. Okay, so if a plus b is even, it means if a is related to b, then definitely b will be related to a. Okay, then definitely b will be related to a. So this is symmetric also. What about transitive? What about transitive property? So here, can I say that R is transitive? The third one is transitive property. What can you say about transitive property? So yes, transitive also. This is transitive also, because you can notice that if a is related to b, b is related to c, then let's check, Can I say A will be related to C? Can I say this? Yes, you can easily say, because from this you can notice that A plus B is even. What it means? Tell me what it means. Tell me what it means. There are two cases. Okay, A plus B is even. There are only two cases. Either both are odd or both are even, right? Okay, so this means there are only two cases. There is case 1 and there is case 2. There are only two cases. What are the cases? Case 1, case 2. Case 1 is when A comma B both are even, and case 2 when both are odd. So either both will be even or both will be odd. Similarly, either both will be even or both will be odd, right? Correct? Okay, so you can easily see that either both will be even or both will be odd. So here also I can say that become both even or both odd. I can say both even or both odd. So you can take two cases, you can take, and you can see in this case also A will be related to C. In this case also A will be related to C. So whatever you do, the A will be related to C. Okay. In this case also A will be related to C. In this case also A will be related to C. In this case also A will be related to C. Okay. In both the cases A will be related to C. So this is transitive also. So finally I can say this is a equivalence relation. This relation R, this is a equivalence relation. Now let's move on. Now let's see properties of equivalence relation. What a equivalence relation does. So let me tell you in this one. In this last example, let me tell you all the properties that are very important. In the class, we have already seen this. Okay. Equivalence relation, we have seen all the details, all the proof, everything we have seen. But let me give you the summary of all the things that are related to equivalence relation. So here you can notice very easily that basically you have a relation R, you have an equivalence relation R, right? So you have a relation R on set of integers. Okay, so this relation, so here what is the base set? Tell me. You have a relation on set of integers, so this is the base set, correct? Okay, this is your base set. Now and this relation is saying that x is related to y if and only if x plus y is even. Okay, if and only if that is even. We have already seen that R is equivalence relation. This we have already seen that this R is definitely equivalence relation. This is done. Okay, now the second point. The second point is very important, that if R is equivalence relation, then what it will do? It will divide the base set into equivalence classes. Okay, it will partition the base set into equivalence classes. This is what a equivalence relation does. Okay, any equivalence relation, whenever you have some equivalence relation on, whenever you have this equivalence relation R on set A, then what will happen? This relation, what it will do? This relation will partition. Okay, on set A, then what it will do? It will partition this A into equivalence classes. Okay, into equivalence classes like equivalence class 1, equivalence class 2, and so on. Okay, so it will partition the set A into equivalence classes. This is called partition of A. This is called partition of A. Okay, so it will partition the A. Partition has some properties, like they must be disjoint. All of them will be disjoint. Okay, all of them will cover the entire A. Okay, all of them will cover the entire A. So this is partition. Partition means they will be disjoint. Okay, if you take their union, then you will get A. Okay, and also they will be non-empty. So this is a partition of A. Okay, so these are some properties. I can easily say that if you have a relation, basically you have a base set, a very simple base set you have. This is the base set A. On this base set A, let's assume you define this equivalence relation R. Okay, on this you define equivalence relation R on set A. Then what will happen? This is your base set A. Let's assume this. Let me assume that this is your base set A. This is the base set A. Now, because of this relation, what will happen? Because of this relation, what will happen? This R will partition. This R will partition. R will partition this A into equivalence classes. Okay, into a set of equivalence classes. A set of equivalence classes. Okay, so this R will partition this A. It will partition like this. Okay, some equivalence classes will be created. Some equivalence classes will be created. So you can see, for example, this is equivalence class 1. Okay, I can say this is equivalence class 1. This is equivalence class 2, equivalence class 3, equivalence class 4. So something like that. Okay, so some partition will happen. Okay, equivalence class 5, equivalence class 6. So like this. And there is some property that all of them will be disjoint. They will be non-empty. And they will cover the entire A. They will cover the entire A. So these are some properties that, let me tell you that these are the properties that all these equivalence classes, they will be disjoint. Okay, they will be disjoint, non-empty, they will be disjoint, they will be non-empty, each of them is non-empty. For example, this equivalence class 1, this is non-empty, and this they are disjoint, they do not have any common element. This and this, they are disjoint. So as you can see from this diagram, you can easily see that equivalence classes are disjoint, they are non-empty, and they will cover entire A. Okay, and they will cover entire A. Remember, they will cover and all the elements, okay, cover entire A. It will cover entire A. Okay, so this is your properties of equivalence classes. I hope you understood. For example, and how can you find the equivalence class of some element? How can you find, if you want to find equivalence class of element A, of element X, how can you find that equivalence class of element X? You can very easily find, this is called equivalence class of element X with respect to relation R. Okay, what this will be? This will be all the elements to which X is related. So Y such that X is related to Y. Okay, or maybe because this is a symmetric relation, because this equivalence relation is symmetric relation, so you can say or Y is related to X. Okay, so both is fine, both is perfect, everything is perfect. So you can notice that the equivalence class of X, that will be set of elements to which X is related. Okay, very simple. Now tell me the answer for this question. What is the equivalence class? In this question I am asking, some questions I am asking, you tell me the equivalence class of 3. You tell me the equivalence class of 3. This is the equivalence class of 3. This notation means equivalence class of 3. What is the equivalence class of 3? Tell me. Can anyone tell me what is the equivalence class of 3? You can easily see 3 is related to 3, 3 related to 5, 3 related to 7, 3 related to 1. Okay, 3 is related to all these things. 3 is related to -1. Okay, -3, -5. So can I say all the odd numbers? Yes or no? Here can I say the equivalence class will be set of all the odd numbers? Yes or no? Set of all odd integers, this will be the equivalence class of 3. Do you agree or not? Okay, equivalence class of 3 will be all the set of all the elements to which 3 is related. Okay, set of all the elements to which 3 is related. You can notice 3 is related to every odd number. Okay, so this will be the equivalence class of 3. The same will be equivalent, this equivalence class of 3, that will be the same as equivalence class of 5, that will be same as equivalence class of -11. Okay, all these will be they will have the same equivalence class. And what that will be? That will be set of all odd numbers, set of all odd integers. Okay, so every odd number will have the same equivalence class. Every odd number that has the same equivalence class. Now let's move on. For example, what is the equivalence class of for example, what is the equivalence class of 10? What is the equivalence class of 10? Can you tell me? This is the equivalence class of 10. So what is the equivalence class of 10? Equivalence class of 10 means all the elements to which 10 is related. 10 is related to 10 because 10 plus 10 is even. 10 related to 12, 10 plus 12 is even. 10 is related to 8 and so on. You can notice 10 is related to -10, -2, 0 and so on. So can I say that this equivalence class will be set of all even numbers? Yes or no? This will be set of all even integers. Again you can notice that what will happen? Every even number will have the same equivalence class. The equivalence class of 2 will be same as the equivalence class of 10, will be same as the equivalence class of 0, will be same as the equivalence class of -20. All the even numbers, they have the same equivalence class, and that is set of all even numbers. Okay, so finally you tell me, in this relation, this relation will partition our base set. This is your base set, this is the base set, you can see this is the base set. Okay, then tell me, this relation R will partition our base set into how many classes? Can you tell me? This relation R will partition our base set. This is our base set. It will partition our base set in how many classes? It will partition into 2 classes. One class will be class 1 and another will be class 2. One class will be basically set of all even, set of all even numbers, I can say. Yes or no? Set of all even integers, because every even integer is related to every even integer, and this will be set of all odd integers. Is this clear to everyone? Please tell me. So there will be 2 equivalence classes. You can easily see that this equivalence relation R, it will partition our base set into 2 equivalence classes. So this is equivalence relation, okay, has 2 equivalence classes. It will has two equivalence class. Okay, it has two equivalence class. Okay, very simple. So now let's move on. So I hope all these points are clear. Now the another thing I want to ask you in this one. So you have two equivalence classes, right? Okay, this relation R, it will partition our base set Z into two equivalence classes, and let's assume, let me call them equivalence classes. Let's call them A comma B. Now can you write this A? Now what you can say? Now this write this R in terms of A comma B. How can you do that? In terms of A comma B. Can you write this R in terms of A comma B? Tell me. So this is what I'm saying, that this is your set of integers, and there are two equivalence classes. One equivalence class is A, another equivalence class is B. Now can you write this R in terms of A comma B? Can you write this R in terms of A comma B? Tell me. Very simple, because you can notice that every element here will be related to itself. Okay, every element here will be related to itself. Every element here will be related to itself. So you can easily write that this R will be A cross A union B cross B. Okay, this will be A cross A union B cross B. Array, A union B will be Z. A union B will be Z. This will be Z. This is the base set. This is the base set. And this is the relation. And this is the relation. This is your equivalence relation. Okay, so this will have ordered pairs. You can easily see this R will have ordered pairs. So this will be A cross A union B cross B. Okay, so this is a simple, very simple thing I want to tell you. Some things, that if you have a relation R, let's assume you have an equivalence relation R. Okay, on set A, and let me assume that some equivalence classes we get. Okay, so let me assume that this A will partition into some categories. So some categories are created, maybe something like this. Some partitions are created. For example, maybe let me assume that this is A1, this is A2, this is A3, this is A4. Then in this situation, what your R will be? In this situation, you can notice that A will be the union of AI. Okay, A will be the union of all the AI. So if you take the union of all the AI, this is an equivalence class. This is an equivalence class. Okay, this is one equivalence class. Now you can easily see that this R will be what? This R will be union of AI cross AI. Yes or no? This R will be union of AI cross AI. It's like A1 cross A1, because every element here will be related to every element here. Yes or no? It is reflexive symmetric transitive. Every element here will be related to every element here. So you can see that union A2 cross A2, union and so on, A3 cross A3, union A4 cross A4. So please tell me, did you understand this? Okay, the complete summary. This is the complete summary of equivalence relations. And I can also ask you the cardinality. Okay, like for example, look at this question. I am giving you a relation R on set A comma B comma C. On this set, let me give you, for example, on 1 comma 2 comma 3, on 1 comma 2 comma 3 comma 4. So I'm giving you a set, I'm giving you a relation R, and this relation R is like this. Okay, X is related to Y if and only if X comma Y, these are congruent to modulo 3. Okay, so now you tell me, in this situation, is this equivalence relation? Is this equivalence relation? You tell me. So first of all, can I say R is equivalence relation? Can I say this? R is equivalence relation? Can you tell me? The answer will be yes, because this congruent to modulo K, this relation is reflexive, symmetric, and transitive. Okay, so all the three properties are satisfied. The reflexive property will be satisfied because X and X, they will have the same remainder, and the symmetric property will be satisfied, and transitive property will be satisfied. This congruent to modulo K, this is a equivalence relation. Okay, so there is this is equivalence relation. Can you tell me what the equivalence class of 1? Can you tell me the equivalence class of 1? Can you tell me the equivalence class of 1? You can notice 1 is related to 1. Okay, 1 is also related to 4. So this is the equivalence class of 1. You can easily see equivalence class of 1 will be same as the equivalence class of 4. Okay, they will be same. Equivalence class of 1, equivalence class of 4, they will be same. Okay, because the same class you will get for 4 also. Again, you can notice equivalence relation is reflexive, symmetric, transitive. So you can easily see that this will be the same. This will be the equivalence class of 4 also. Now, Okay, now what about the next? For example, in this, you tell me the equivalence class of 2. What is the equivalence class of 2? So 2 is related to 2 only. That's it. Okay, so equivalence class of 2 will be 2 only. And you can tell me what is the equivalence class of 3? Equivalence class of 3 will be 3 only. Right? Okay, equivalence class of 3 will be only 3. So you can easily see that how many equivalence classes we got. Can you tell me how many equivalence classes we got? So what is the number of equivalence classes for R? For what is the number of equivalence classes for R? That will be 3. Okay, you got 3 equivalence classes. Now what will happen? See what will happen, that this will partition. This is your base set. You can easily see this is your base set 1 2 3 4. Okay, let me call it set A. Let me call it set A. So this is your base set. Okay, so this base set has been divided into 3 parts. Okay, into 3 classes. In one class you have 1 comma 4, in one class you have this, in one class you have this. Okay, so you can easily see, let me call it, for example, let me call it P, let me call it or maybe I can call it M and P. Then in this situation what will be A? A will be M union N union P. Okay, this will be the A. But what will be R? But what will be R? Tell me, this is simple question I am asking. What will be R? In this, what will be R? R will be what? R will be M cross M, because every element here will be related to every element here. Union N cross N, union P cross P. Okay, so this will be your I can say relation R. So you can easily see what is the cardinality of the relation R. What is the cardinality of the relation R? Can you tell me? In this R, how many elements we have? What is the cardinality of the relation R? So the relation R cardinality will be very simple. That will be cardinality of because what is happening here? See what is happening here. You have these equivalence classes. As you can see, this is your set A. Okay, this is your set A. Now you have these equivalence classes, like you have M where you have 1 comma 4, you have N where you have 2, and you have P where you have 3. So these are the equivalence classes. Now with the cardinality of R, in the R what will happen? In the R, this type of pairs will happen. See, 1 will be related to 1, 4 will be related to 4, 4 will be related to 1, 1 will be related to 4, and 4 will be related to 4. Similarly, 2 will be related to 2, 3 will be related to 3. So the cardinality of this relation R, you can easily see that is 6. Okay, that is a 6. The cardinality of this relation R, that will be cardinality of R will be 6. You can easily find this 6. How to find this 6? Because you can easily see that if you have relation R, if you have a equivalence relation R, this is the last note. So if you have a equivalence relation R, okay, on set A, so here the base set is A. So here this A is the our base set. So the partition will happen for what? For R or for A? Whose partition will happen? Whose partition will happen? So you have a equivalence relation. You have a equivalence relation. Then partition of A will happen. Correct? Okay. This A will partition. This R, because of this relation R, this A will partition into some categories. Okay, into some equivalence classes. Number of equivalence classes can be finite or infinite. Okay. Remember, number of equivalence classes that can be infinite also. Okay. Now here I am saying that, for example, you have M here, or maybe you can say this is A1, this is A2, this is A3, A4. Then in this situation, the cardinality of R that will be equal to what? Just do the summation of for every this is what you do. You do the summation of cardinality of AI cross AI. Okay, this is what you do. That's it. So just do the summation of cardinality of AI cross AI, because here every element will be related to itself, here every element will be related to itself, and so on. So this is the complete summary. I hope you understood all the properties of equivalence relation. Did you understand all the properties? We have seen all the properties of equivalence relations. For example, as you can see, the equivalence relation will partition our base set into some classes. Yes or no? For example, your base set is set of shapes. Okay, so here your base set, in this example you can easily see what is your base set. In this example, what is our base set? Our base set is set of shapes. Set of shapes. So this is our base set. Now you are defining a equivalence relation. X is related to Y if and only if they have the same shape. So this R is definitely equivalence relation. This is a equivalence relation. Now you can easily see that the base set has been partitioned into different equivalence classes, correct or not? This partition has happened, that they have the same shape. Okay, so the partition has happened, they have the same shape, they have the same shape, they have the same shape. Okay, so you can easily see the base set will partition into equivalence classes. So you can say this is equivalence class 1, you can call it this is equivalence class 1, this is equivalence class 2, this is equivalence class 3. Okay, so like this. So there are 3 equivalence classes. What is the cardinality of this relation R? Can you tell me? Can you tell me the cardinality of this relation R? For this relation R, what is the cardinality? You can notice every element here will be related to itself. So from here you will get 3 into 3, 9, plus every element will be related to itself. So from here you will get 4. See, here you will get 9. Why? Because it will be related to itself, related to itself, related to itself. Next, it will be related to this, 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 and so on. So from here, from this equivalence class, you will get 9 ordered pairs. From this equivalence class, you will get 4 ordered pairs. From this equivalence class, you will get 9 ordered pairs. Okay, so finally the cardinality, you can check it out, that will be 9 plus 4 plus 9, and that is 22. Very good. Okay, so very good. Now let's see this one. So again here the same thing is happening. What is the base set? The base set is again set of shapes, yes or no? Again, what is the base set? The base set is same. The base set is a set of shapes. This is the base set. The base set is a set of shapes. Now you are defining a relation R, and this relation R is that X and Y have same color. You can easily see this is reflexive, symmetric, transitive. So again, this is an equivalence relation. Again, you can notice this is the equivalence relation. Now in this equivalence relation, what will happen? You got some categories. See, this equivalence relation T, this relation T, this relation T, being the same color, okay, being the same color, this relation T has divided our base set into some classes. Okay, it has divided our base set into some it has basically it has partitioned our base set into some parts, into some equivalence classes. Like you again, you can notice this is your equivalence class 1, this is your equivalence class 2, this is your equivalence class 3. So your base set has been divided into some equivalence classes. Your base set of all the shapes, that has been partitioned into some parts. Okay, now again here the same thing. Again, you can notice that all these have the same color, all these have the same color, all these have the same color. Okay, so like this. I hope all these points are clear. So I hope you understood the equivalence classes. What is the equivalence class? Equivalence class of some element, if you want to find for element X, what is the equivalence class? That will be set of elements which are related to X. Okay, very simple. Now let's move on. So as you can see, this is the equivalence class of this. This is also the equivalence class of this. Okay, so if you look at this equivalence class, so look at this equivalence class. This is equivalence class of yellow also. This is equivalence class of this also. This is equivalence class of this also. Similarly, this equivalence class, this is the equivalence class of this star also, this star also, this star also. Okay, I hope this point is clear. Now let's move on. So this we have already seen that if you have an equivalence relation on set A, then every element will belong to exactly one equivalence class, right? Every element will belong to exactly one equivalence class. This we have already seen. Okay, this we have already seen. Whenever you have equivalence relation R on set A, okay, whenever you have this, then this will happen. What will happen? This is your set A. It will partition into some parts. Number of parts can be finite or infinite, but this will happen that you can notice these are the equivalence classes. This is equivalence class 1, this is equivalence class 2, this is equivalence class 3, equivalence class 4, equivalence class 5, and so on. There can be more equivalence classes. You can have infinite number of equivalence classes, but the point is very simple, that these are disjoint, these are non-empty, and they cover all the elements of A. So basically I can say that for every I can say what will happen for every element of A, what will happen? This A will belong to exactly one equivalence class. A belongs to exactly one equivalence class. Okay, let's move on now. The next concept is irreflexivity. When can I say a relation is irreflexive? If no element is related to itself. Okay, no element is related to itself. No one is related to itself. Okay, like for example, this is irreflexive. You can notice no element is related to itself. So this is your irreflexive. Now let's see this. So remember, first of all, is it possible same relation can be reflexive and irreflexive? Some questions I am asking. Is it possible, can, this is a question I am asking, can R be both reflexive and irreflexive? Can relation R be both reflexive and irreflexive? Can it be both reflexive? It is reflexive also, it is irreflexive also. The answer is no. Okay, because if you have a relation R on any non-empty set, on any non-empty set, then what will happen? This reflexive will say that A should be related to A. This reflexive will say that this should happen. And irreflexive will say that A should not be related to A. A should not be related to A. This is what irreflexive will say. So irreflexive saying that no one related to itself. Okay, irreflexive is saying that no one related to itself. Reflexive saying that everyone related to itself. So you can easily see that this is not possible. Okay, reflexive and irreflexive, same relation is reflexive and irreflexive. That is not possible because reflexive means everyone related to itself. Okay, everyone related to itself. Irreflexive means no one is related to itself. Now let's see, can a relation be, can R be neither reflexive nor irreflexive? Can a relation be neither reflexive nor irreflexive? Is it possible that it is neither reflexive nor irreflexive? Yes, this is possible. This is very much possible. For example, you can consider this example, A, B, C, D. Okay, let me assume that you have this type of relation. Let me assume this type of relation you have. Now you can easily see that this is not reflexive. This is not reflexive. Why? Because B is not related to B. Okay, and you can notice this is not irreflexive. This is not irreflexive because A is related to A. So remember, very simple, irreflexive means no one related to itself. Reflexive means everyone related to itself. Okay, so these are not completely opposite of each other. Okay, remember, so reflexive and irreflexive, these are not completely opposite. I cannot say that irreflexive. Can I say not reflexive means irreflexive? Can I say? Can I say not reflexive means irreflexive? Can I say? This is a false. This is false. Okay, so it is possible that not reflexive may be not irreflexive also. So remember, very simple. For example, here it is not reflexive, it is not irreflexive. Okay, not reflexive, not irreflexive. So these are not completely opposite of each other. Reflexivity says that everyone is related to itself. Okay, for every element I am saying A is related to A. Negation of this not reflexive. Not reflexive means someone is not related to itself. Someone is not related to itself. Irreflexive says that everyone is not related to itself. Okay, let's move on. Now the next concept is asymmetry and antisymmetry. So let me take this. The next definition is asymmetric, antisymmetric. What are these relations? So when can you say that a relation is asymmetric? Asymmetric. When can you say a relation is asymmetric? This is also called countersymmetric. Another name is countersymmetric. So when can you say this asymmetric? And what can you say antisymmetric? So asymmetric means, asymmetric, it simply means that no reflexive pairs. First of all, no reflexive pairs. Okay, it simply means that there are no reflexive pairs. What it simply means? It simply means that A is not related to A. Okay, for all A, I am saying for all A we can say that A is not related to A. The second point that if A is related to B, then B is not related to A. Okay, if A is related to B, this is what I am saying. If A is related to B, then B is not related to A. So very simple. So asymmetric means, remember, this line is already included here. Okay, this automatically means that no reflexive pairs. So this is the definition of asymmetric. I hope this point is clear. Remember, this automatically means no reflexive pair. this automatically means that there are no reflexive pairs. So I hope this point is clear. Means if A is related to B, then B should not be related to A. This is the asymmetric. Now what is antisymmetric? There is something called antisymmetric. What is that concept? Antisymmetric. In antisymmetric, the same as asymmetric, but reflexive pairs are allowed. Okay. Basically, antisymmetric means the same as antisymmetric. So antisymmetric is same as asymmetric, but reflexive pairs allowed. Okay, reflexive pairs are allowed. Okay, these are allowed. Means reflexive pairs may be there. We don't care about the reflexive pairs. So these are allowed. Okay, same as asymmetric, reflexive pairs are allowed. It may have reflexive pair. So what is the definition of this antisymmetric? Let me tell you. This is important. So this definition is very important. Which definition? So for antisymmetric, the most popular definition, the most useful definition is this. That we are saying that if A is related to B and B is related to A. Okay, if A is related to B and B is related to A, then what should happen? Okay, if A related to B, B related to A, then definitely they must be same. So if you have symmetry, that must be between same elements. Okay, so if A related to B, B related to A, then what should happen? Then A should be equal to B. This is the definition of antisymmetric. Or you can use this definition. This is the very important definition. Remember, this is the very useful definition. Another definition is if you have two different elements, then okay, if A is not equal to B, then it can never happen. Then it can never happen. So I can say A related to B, B related to A can never happen. Okay, this and this I can say both cannot happen. Okay, at most one of them will happen. I can say then at most one of them will happen. Then at most one of them can happen. Okay, this is the definition of antisymmetric. Antisymmetric means same as symmetric, but reflexive pairs are allowed. It means if you have a symmetry, A related to B, B related to A, then that must be between same element. Okay, then A comma B must be same element. So if you have different element, then at most one of these things can happen. At most one of these. Okay, at most one of these things can happen. At most one of them. Now let's move on. So this is the definition of asymmetric and antisymmetric. Now let's move on. So we have already seen that if A related to B, then B not related to A. This is the concept of asymmetry. For example, this is the asymmetric. You can easily see this diagram. You can easily see this is asymmetric. You can see there is no reflexive pair because asymmetric does not imply, allow reflexive pairs. So you can notice there is no reflexive pair. Okay, the reason is asymmetry. Asymmetry does not allow the reflexive pair. You can see this pink is related to yellow, but yellow is not related to pink. Okay, so very simple. Now let's move on. So what about this question? Tell me the answer. Tell me the answer for this question. Let R be a relation which is given by this photo, by this diagram. Then what is correct? R is reflexive. This is not correct because you can easily see this is not related to itself. Okay, R is not reflexive. Yes, this is correct. It is not reflexive. R is irreflexive. This is not correct because of green. So this is the violation of, you can easily see this is the violation of irreflexive. And this is the violation of reflexive. This is not irreflexive. Yes, this is correct. Okay, so not reflexive, not irreflexive. Let's move on. So all the definitions we have seen, I hope you understood.